Here you have
Hey,
yes,
I
15 minutes
just
to
share my
5.
screen.
Yes, it's fine. It's not full screen, huh?
Yeah, I will put it in this. Mm, mm, mm. Now that you can see that the full screen mode.
Yeah, it's perfect.
Cool. So should I start?
Yeah, you can go. Up to you.
Okay. So hello everyone. Good morning. For those who doesn't know who I am, I will introduce myself. I am Margarita Pereira. I'm part of the Mexican collaboration, and I'm currently working at the Institute of Astronomy of UNAM, but not in Mexico City. I'm working in Ensenada, very close to the San Pedro Martir Observatory. And today I will talk to you about this particular event here, which is the GRB191016A. And the purpose of this talk is just try to convince you that in the Mexican part of this collaboration, we are ready to take the most from Colibri when it is finished, installed, and properly working at the observatory. And the way I will I'm planning to do that in this talk is to show you how we are now currently taking advantage of the instrumental capabilities in San Pedro Martir. So first of all, I will introduce you the three of the instruments that we regularly use to perform GRB observations. Those instruments are Coatli here and Ratir, which is mounted on the 1.5 meter telescope in San Pedro, and the newest, which is Doti, that Rosa had talked about before in this workshop. The main characteristics of each of these instruments are listed here. And for instance, Coatli is one of the instruments that we use to perform early time observations because it is a fast response telescope. With Ratir, we usually do optical and near photometry, near infrared photometry. And this instrument allow for photometric redshift estimates. And also the higher sensitivity from Ratir cameras allows for late time observation. With Coatli, sometimes is limited at the end, particularly at the end of the afterglow emission of GRBs. And for Doti, just to mention this, as Rosa already did, is a wide field imager, which is dedicated to locate Fermi GRBs and gravitational wave counterparts. Okay, what do we usually look for in this data, the data from these instruments? Well, with those data, we can construct Lie curves. The Lie curves associated to GRB events are in the general framework of the fireball model. They are composed or formed by three different main features, which is the electromagnetic counterpart in high energy emission, which is properly the GRB, the gamma ray burst, associated to internal shocks occurring in the band. Afterwards, we have the afterglow emission, which is related to the external shock, essentially the interaction of the head of the jet with the external medium. And sometimes if we have sensitivity enough and we have lucky to observe a supernova too. This afterglow emission is the one that I will present you for the GRB 191016A, because this is the part of the Lie code that we were able to describe in a very nice way with the data acquired with the instrument in San Pedro Martir. So the story for this GRB started with the SWIFT path alert. SWIFT detected GRB in the high energy range, which is the Lie curve is shown here. we can see from this clearly a multi-peak light curve, which is a long duration GRB, which classifies the GRB as a long one. It's a long type GRB. After, and this part is that the one that will be being performed by SPM when it is launched and ready to observe. And the part where we expect to make use of Colibri is for the afterglow emission that we are currently characterizing using two instruments. One is Coatli with the fast response that I mentioned. And with this instrument, for this GRB particularly, we have the first detection, and we were the first team to report the detection of an afterglow candidate, which was confirmed afterwards for other teams around the world. And this is the detection indicated with the blue arrow here. This is part of the Coatli field from that night. After we had this confirmation of the afterglow, we continue with a follow-up campaign from San Pedro Martyr using Coatli and also Ratir, which goes from 0.1 to 8.5-ish hours after trigger time. And also we have with Ratir particularly all late time observation for the two subsequent nights. This is the light curve that I showed you previously, where the white dot here are the Coatli data, and all the color one, except for this one, which is dotty, correspond to the Ratir filters. So this data allows to build a complete characterization of the optical afterglow, which is the plot I'm showing here. The first part of the light curve is well described with the Coatli data, which is the fast response telescope, and it can have a good cadence to describe in a very nice way all the rise of this particular afterglow. We have we identify 5 different phases, which are the rise and early decay, which is showing here, plateau phase, a late subsequent late decay, and also some evidence from for a jet break, which is is possible to infer from here thanks to Ratir data. So when I showed you this previous light curve, you may think that it seems to be easy to get this complete or description of light curve and afterglow, but as I told you before, you really need fast response telescopes and high sensitivity to do that, which is what Colibri is bringing us in the future. So to show you an example on how this is not easy and why Colibri is really important for us in the future is that we have 2 other light curves from some previous work about the same GRB. These light curves are from the GRB191016A. And you can clearly see from this, which is a test light curve, which is only capturing the rise and the decay of the light curve, but the other features that I mentioned as the jet break and the plateau and a late decay are not in any way easy to identify here. So the other light curve that is being published for this GRB is one from using data from the Liverpool telescope and plus some information gathered from the GCN network. And even though they have a very nice coverage in this part of the light curve, which is the early decay and part of the plateau phase that I mentioned before, they have very few data points for the rise. They have lack of data around the peak time, and also for the jet break, the data are not homogeneous mainly because they are taken from the GCN information directly. So that makes this light curve that we acquired with San Pedro Mártir telescope the best description of the afterglow light curve to date for this particular GRB. So the other thing that we can do with the observation from San Pedro is particularly with RATIR, which is an instrument that allows for simultaneous RATIR, simultaneous observations in different filters, is to try to obtain a redshift determination. This is what we did using around 3 kiloseconds exposures time here, which was simultaneous from 6 to 10,000 seconds after trigger. We use this data to construct, build the spectral energy distribution for this GRB and try different models, extinction models, to obtain a redshift. We found that the best fit for this GRB was obtained using an SMC extinction law, which placed the source relatively high redshift around in a range of 2.4 and 3.3 in C values. So when we have this information from our data, we started trying to understand what's the physics behind the events. So the first thing that we were able to do that other people couldn't do because of the lack of data was to determine the exact peak time and compare this time with the whole sample, a bigger sample of GRBs, which is shown in this plot here, which is a distribution of time peak for different GRBs is around a sample of around 100 GRBs. And what we learn from this is that even though it seems to be a late peak time, or relatively late peak time, is not particularly peculiar when we compare this with a general distribution of many other GRBs. If we take just this without correcting this into the rise frame of the GRB, it belongs in a kind of average population. Here is not the most common, but is not either an outlier on the tail of the distribution. And if we consider the redshift estimate, we can place it here into the common ones or the most regular T peak time observed for the optical afterglow with rising light curves. The other thing that we were able to do for this GRB is to propose a theoretical model to explain all.
Just 3 minutes left.
Sorry,
We are just
3 minutes.
3
Okay.
minutes left.
Yeah. Yeah, thank you, Stefan. We propose a theoretical model to explain the different phases we observe in the light curve. This is data. This is the model that we are proposing. And essentially, we explain this rise and early decay with a superposition of power shock with a substantial contribution of the around the peak time from an embedded reverse shock. And the plateau phase and the late decay and jet drake need some additional components in the mission, which we include as a late energy injection by the central engine, and the inference of a jet brake here occurring between 2 and 12 hours after triggered battery, sorry. From this model, we can also try to determine some of the properties of the fireball, such as the Lorentz factor, the opening angle of the jet, and property of the fallback rate, producing the late injection. So to conclude this, I hope I showed you a good example of what we can do, what we are currently doing with the telescope in San Pedro, and what we will able to do when Colibri is finished. So Colibri will be filling this gap that we will have, unfortunately, next year's with Ratir, because the instrument is being removed from that the telescope where it is currently mounted. But that's why we are very looking for Colibri, and it will allow us to make light curves for a complete description of the optical behavior of afterglows of GRB, redshift estimates, also late time observations for look for the jet break, and of course increase the number of detection for GRB optical afterglows. And the theoretical part of the collaboration, of the Mexican collaboration, is also ready to analyze this data with us. And that's all from our side. So thank you so much for your attention, and we are very looking forward for Colibri to be ready. Here are some names of the people that we are waiting for it to happen. Thank you so much.
Thank you very much for this very nice talk. Damien, you have a small question?
Yes, thank you very much. It's exactly what we want to do with Colibri. But of course, we have not the same capacity as Ratir. What will happen to the instrument? Because the instrument is super nice. And do you plan to mount it on other telescope? Is there what? Maybe I don't know if you know, or maybe Alan know.
Maybe Alan can comment on that more than.
Yeah, we have an agreement to keep Ratir on the telescope until next summer. And beyond that, it's not clear what will happen. I suspect another instrument will take its place. So I don't think we should plan to be operating Colibri in parallel with Ratir.
That's right.
I'd also say that you commented that Colibri won't be the same as Ratir, and that's true, but I think it will be very competitive. I mean, we'll have 3 channels instead of 4. Okay, but we'll have the same filters available, you know, G, R, I, Z, Y, J, and H. And a big limiting factor we have in Ratir is that the cold head vibrates the telescope and vibrates the secondary. And so we end up with 2 arcsecond images. I would hope that we get better images with Colibri. And so I would hope that Colibri is more sensitive than Ratir. I'd also comment that, you know, one of the things Maggie mentioned is that Ratir is on an old telescope that takes 2 minutes typically to salute an event. Quantly will be there in 10, 15 seconds. So, you know, that's a huge amount of science we can do with a big telescope, relatively big telescope, getting onto sources quickly.
Mm-hmm.
No, I completely agree. I didn't say that. We will not do anything, anything with Colibri. I already hope that we will do as much as Ratir and even better for the early time.
Yes.
Jean-Luc, you have a comment, a question?
Yes, I had a question about the modeling you showed. What kind of tool are you using? Is it custom tool or something, this Python, I don't remember, Python afterglow model or something like that? How do you do that? For the modeling of the afterglow?
I'm using Steam, so I'm not sure if the Steam is here. So, but as far as I understand, is a kind of custom tool that Nassim is using for modeling these light curves. But to be honest, he's the one to answer that question, I guess, but I'm not sure.
Okay,
he's around.
Thank you.
I don't think he is. But I can happily pass the question and let you know. Yeah, Rosa, please.
Typically, what Nassim does is to put the luminosity at certain time in optical, in X-ray, and compare with our alpha decays parameters, and try to estimate the energy and the opening angle, and also the opening angle or the Lorentz factor. And try to make a chi-square study, and that's it. The technical stuff, I don't know.
No, but okay, this clarifies, this answers my question.
Yeah, it's all the, if I may, it's all the, the synchrotron modeling in different regimes for the different shells and or the component of the reverse shock, etc., and the microphysical parameter modeling. That, and Nissim Freya is the one who takes care of that.
Okay, thank you very much.
We have a last question from Robert.
Yes, thank you for the talk. I suppose you don't have good XRT data for this birth, and it is a pity because it would have provided very useful information. There is nothing from the XRT?
No, unfortunately, well, there is some, but they are the one that I show at the very end of the decay. The problem is that SWIFT has some mount constraints for observation in that time. So the first 12 hours of the afterglow emission, they couldn't, the satellite couldn't slew to the field because of mount constraints. So the only data points that we have are at the end.
And you can do nothing useful with those few points, I suppose. You
Yes,
would have needed the beginning of
stuff.
the evolution, which is lost.
Yes, but they actually, even if they were few data, they were useful for the inference of the jet brake, because we, I can show you the, let me go back just quickly. So if you see here, the data, they are after 12 hours. With these points, we kind of constrained the temporal slope here, which is in fact very consistent with our optical data here. So we use those data for that. Yeah, it's a shame that we missed the whole thing, but yeah, even though they were
okay,
useful.
thank you. It's a pity that we have missed the early X-rays because it would have provided very useful information. Unfortunately, we don't have them. Thank you very much.
We do better with them. So now it's time.
Let's hope for the best.
Yes,